tonight. So a lot of you have probably seen this before as well, but we are the Atoms to Galaxies group. We are supported by the University of Southampton and Mendeley, but we've also got a huge global organisation behind us. So we're all PhD students at the University of Southampton, but this is a festival that's happening worldwide, Pint of Science, getting people in pubs talking about science. So if you're a scientist and you want to manage your references, then Mendeley are the people that you go to manage your references. And if you're not a scientist, or you're not in academia anyway, then you probably don't bother with Mendeley. But if you could tweet to Mendeley tonight that you're enjoying this event because they're supporting us, that would be fantastic. And yeah, it will help us out as well in being able to put more events like this on in the future. Right, so tonight we've got a brief welcome. We're going to try to stick to time tonight, roughly. I had a few nightmares of deja vu and the laptop started to go wrong again.
Skip the slide.
Skip the slide, fair enough. That slide, that was the slide I skipped, right, okay. So I've been now told that we have a 90% confidence rating that these questions at the beginning are going to work. So 90% chance that when you hit an answer on the buzzers that you have been given as you came through the door, you can actually answer this question. So how many people here tonight are scientists is what we want to know. So based on the answers up here, let's get an answer. I'm so much crossing my fingers now. 90% confidence. Do I have to press another button, Rob?
You just click it on one slide, it'll show the graph.
Oh, hello, okay, we've got a graph. Okay, now we're 99% confident. 54% non-scientists. I don't know how many of you have answered. I'm probably going to have to ask you to put hands up if you've answered. 37 people have answered. Okay, so we've got a fair number of people here who are not scientists and are here to engage with scientists, but we've also got a fair number of scientists in the room who are here to answer your questions. That's fantastic. Okay, so rudest question ever. Enter your age category, but it's all anonymous, so it's great, it's fine. Nobody wants to answer how old they are, funny that.
Might need to reply to that.
Is it?
You can't go back.
I can't go back. So, okay, right. So I get rid of it.
Click on once.
And click on once. And again. No. Nobody wanted to know. It was a rude question. I'll skip on.
This one will work.
This is definitely going to work. That's a 99% confidence rating I can hear right there. So what's the highest level of education achieved? Again, I'm so sorry for these questions. But it's testing the zappers. Okay. I can't actually read the answers. That's brilliant. But yeah, a lot of you went for the undergraduate degree. That's great, fantastic, well done. But yeah, lots of interest there. Moving on. How did you hear about us? That's an interesting one. I'm actually interested in how you heard about us, so I'd really appreciate answers to that. Can you all read it, by the way? Do you need me to read the answers out? I do apologise. So, TV or radio is A, B is print media, C, web search, D, Twitter, E, Facebook. Is this not working again?
You might have skipped ahead too quickly, so if you
okay.
When you get onto a new thing, just click it once. If you go twice, it closes the poll.
I definitely only clicked it once.
Who knows?
Who knows?
I'd say 90%.
90%. So yeah. Okay, so this is a really good one that we liked last time anyway. So which adjectives best describe scientists and science and scientists? Reliable and trustworthy is A. Critical and essential. Oh, people have already voted. Okay, we're critical and essential. I like essential. Complex and fascinating as well. That's good. Relatable and close to people. Well, hopefully we can fix that tonight. Nobody's thinking we're particularly relatable, but we're trying to fix that. And nobody thinks we're boring, so that's good. But I'm fairly sure that none of you will think we're reliable and trustworthy in tonight either. Anyway, we are already running over time, so I am now going to pass on to Hendrik Ulbrich to give our first talk. Hendrik is here. So Hendrik did his PhD, I think, in the University of Vienna. And then you spent some time in Germany basically making big small things go through gratings. Now you're in Southampton making bigger small things go through light gratings.
Yes.
I think that's just about right. I'll hand you over to Hendrik for more.
Okay, thank you.
Thanks a lot. Thanks for having me. Can you hear me? Yeah? Okay. So the slides will be up in a second. Okay, so I wanted to talk about matter waves because the topic was waves. There was some confusion. I submitted 2 abstracts and then someone else choose what I should talk about. So, I take this and I talk about matter waves. So where's the clicker?
Where's Max?
So oh, you have it there. Great stuff. This one. Okay. So waves, right? They're there, and that's a very common concept which we use in physics to describe stuff. And many of you are scientists. But I guess all of us have seen this. So what this is a look on the water pond. So there are ripples on water. So I'm not used to a microphone. I feel a bit like Madonna. I know I'm less attractive, but it feels strange. Anyway, so there are ripples on this water. And the question is, what is actually an experiment to see that you have a wave? And the experiment, of course, you all know, so I try to pick you up on something which you know from your everyday life. So you know interferometry experiment to prove that you have a wave. Yeah? And what you see in such a double slit experiment where you have these 2 slits is an interference pattern. What happens here is that you have so-called plane waves with plane wavefronts which are moving in this direction, and then they're hitting this double slit. And then you disturb the wavefronts, you form 2 spherical waves, they overlap and they interfere, and then you can have this stuff which you also know, of course, if you look in different directions. Oh, I'm destroying the setup. If you look in different directions, you can have this constructive interference. Yeah? So basically the 2 waves which go separately through the slits, they overlap, yeah? So that we say that they're in phase. Yeah, so which means that if you look at wave 1 and wave 2, they have basically the minima at the same positions and the maxima also at the same positions. And if you add them together, if you superimpose them, then you get another wave which has a larger amplitude. So you basically see a large contrast of bright and dark fringes. Yeah? You can also have the opposite effect, which is this destructive interference. And then you have just along different directions, so I think if I click again, then that's the blue directions. You again have these 2 waves. Yeah? Now they have a different relative shift, and you find that the minima here finds a maxima there. And then you cancel out these waves. Yeah? So therefore you don't have any modulation of this brightness along those lines. Yeah? So that is interferometry. The easiest way to explain, if you basically observe this modulation of the intensity here, is by using a wave as a concept or as a model for the phenomenon which you observe. Okay, so now that is a purely classical example. It's a classical wave on water, but you have the same kind of physics, the same effect in light. Of course, you all know that there's this famous light interferometry experiment, Young's double slit experiment. So what you can do is you can also use light source, again plane wave, yeah, plane wavefronts, and then you have something there which can be a double slit. It can be an object which has somehow a length scale which is on the order of the wavelengths of the wave which you use, and then something happens to the wave, and that is diffraction, and you again see interference pattern and things like that. Yeah. And that is actually the experiment which proves that light is also a wave. Yeah? So now that is interesting. So we say that light is a wave because we can diffract it. So again, that's a completely classical experiment because we have here light described by an electromagnetic wave, which is the classical concept of light. Does any of you know what makes this experiment a quantum experiment? So what would be different in this experiment if we would have a quantum interference experiment? Yes, exactly, that's the point. So you don't have a wave anymore, you have a single light particle, which is a photon, yeah, which basically hits this object, and then you have this, difficult task to explain how a single object, yeah, which, can be a particle, a photon, a light particle, how can that basically do this interferometry trick? Because what you see is if you repeat this experiment, yeah, with a single photon many, many times, yeah, so you always have only one photon in this position here, but you do this 1,000 times, 10,000 times, a million times, then you get exactly the same interference pattern which you get for the light wave of the same wavelength. Yeah? And that is somehow puzzling because it means that somehow the single particle here has to be in two different locations or something like that, yeah, at the same time. And that is called quantum superposition. And that is one of the very intrinsic features of quantum mechanics, that you have this quantum superposition principle that, for instance, a particle can be at two locations at the same time. Yeah? So that is something which is not known in classical physics, so I cannot go through two doors at the same time, and I cannot do two things at the same time. Yeah? But in quantum mechanics and for small particles, that's possible. Okay, so again, what you use now in physics is, obviously you struggle in explaining this single particle quantum experiment with really a particle, so you need a different object, and that is more like a wave. We call it a wave function, but from the concept, it's more like a wave. Yeah? So if we do this quantum experiments, we basically prove that also in quantum mechanics, things behave like waves. Yeah? And now that brings us to meta waves. Yeah? So I have talked a lot about waves, but I have not mentioned meta waves. So what is a meta wave? And that brings us to this gentleman here. So that is Louis de Broglie. Yeah? So he was a prince in Belgium, I think, and he is very famous. He got the Nobel Prize for this equation. And he wrote his PhD thesis, which was, I think, less than 10 pages, and he wrote a paper which got him the Nobel Prize, which was less than 1 page. Yeah? So that is efficiency. Okay, and he invented this equation. Yeah? So almost out of the blue, he said, also every particle which has a mass, yeah, not only photons, also electrons and atoms and molecules, and in principle everything which is really large has a wavelength. We can associate the wavelengths to this, and that is this guy here, which is now called the de Broglie wavelength, after this guy. Okay, so now this equation is very interesting, because you see here is, in this, if you just concentrate on this part here, that's the only equation which I show. Yeah? So here is the wavelength, yeah, which is a property of a wave. Yeah? On the other side, there is P, which is the momentum, which is a property of a particle. Yeah? That is basically, if you have a particle of a certain mass, how fast is this particle moving? What is the velocity of this particle? Yeah? Momentum is mass times velocity. So that's a particle property. So we have this equation, which basically combines wave properties with particle properties. And the thing which combines it here is this Planck's quantum. So whenever you see this H in an equation, that tells you, there's something with quantum mechanics, because that's basically the unit which quantizes all the stuff in quantum mechanics. So that's a very famous equation. But what does it mean? Yeah? So now if you have an object, is it a wave or is it a particle? So people are not sure, and what they say, there's this so-called particle-wave duality. So if you do some experiments with an object, then it shows wave properties. If you do a different experiment with the same object, then it shows particle properties. Yeah? So wave and particle is both possible, and I think, on a very fundamental level, it is not clear to anyone what actually, the basic constituents or the basic, building blocks of nature. What is it actually? Yeah? So it's really not very well understood, and I think that's the closest we are towards this question. So I want to spend the rest of this, I don't know how many minutes I have left, to talk about those meta waves, to talk about the experiments which people did historically and also more recent to actually check if this equation holds. So you have basically a beam of massive particles. Yeah, so massive particle means this object has a rest mass which is non-zero. So the photon has a rest mass which is 0, but the other particles, which we not high energy particles, so that's too complicated for me, but the simple stuff which starts with an electron and a neutron and an atom, these are massive particles. That's what I mean when I talk about massive particles. Okay, so now he would much probably not have received the Nobel Prize, yeah, if there would have been no experiment to prove that this is right. And the first experiment was this one here. I love this a lot, by Davidson and Germer in Bell Labs in the States. And they started in 1925 and did a series of experiments until 27. And then they published a paper and they showed an interference pattern of electrons. Yeah, so the interference pattern of electrons you can see here, basically it is the same stuff which you saw on the previous slide. So you have regions where you have, a lot of electrons, and you have regions where you have no electrons, and the modulation depends on the wavelengths of those electrons. Okay, so here's the setup. I love this really a lot because here you can see really, the nuts and all the details, how they have built this. And I can imagine, being an experimental physicist, how shaky and floppy this setup was and how many times they have tried to, get it right and get it aligned and all this. So there was a lot of sweating, I guess. Okay, so to tell you the details a bit more, there's this here, what they call the gun. So there's a little needle, which I hope you can see, which is the electron source. So that is basically a metal wire, and they apply a potential between this metal wire and an electrode here. Yeah, a voltage, I think they use something like 50 volts or so, and then a process which is called field emission happens, so electrons from the tip come out, and then they have a number of ring electrodes and collimation slits to actually form a directed beam, yeah, so that the electrons don't go in all directions, but that they really just fly in the forward direction. They send this beam on this target, which was a nickel crystal, yeah, and what now happens is that basically the atoms which are arranged in this nickel crystal act as a grating for this matter wave. Yeah? And then they have here the detector which they can move, so they can basically measure the electrons which are diffracted, or if you want, scattered in different directions. Yeah? And now the scattering signal is exactly this, and as I said, it depends on the wavelengths of these electrons, which depends on the speed which they have, on the velocity which they have, and the mass. And it also depends on the lattice constant of this material, so how wide these electrons are separated. So now, that is a very complicated experiment even today, but they had to do it, and they needed this atomic structure of this nickel, because the wavelengths of the electron is very small. Does any of you have an idea roughly what the typical wavelengths, the de Broglie wavelengths of an electron at this energy is? Yeah, it is. I would guess it's on the range of nanometers. Yeah, so 10 to minus 9. It's really small, and that's why they had to use this structure. Okay, so that was 26, 27, and that was the proof that these matter waves really exist. Yeah, so indeed electrons behave as waves, which was good for de Broglie. He got the Nobel Prize, but also these two guys, they got the Nobel Prize as well. So it was a big celebration. Now we make a big jump. That is last year in Stanford, Mark Kasevich group. They do atom interferometry. So what they do is they do principally the same experiment. 3 minutes. Okay, 3 minutes and 5 slides. Okay. So they have a fountain. That's an amazing experiment. So what you see here is 10 meters. So they have a vacuum chamber which is 10 meters high, and they shoot a cloud of cold atoms in this direction, and then they build a matter wave interferometer. So they basically, if you think of this, I don't have my second hand, it's really so they take in principle a single atom, I think it's a rubidium atom, and they shoot this up, and then they interact with light pulses, and the light pulses do a very fancy operation on the position of the particle. They generate this so-called superposition state, yeah, like in a double slit, and the separation they achieve here, yeah, from being higher and lower, is half a meter. Yeah, so they basically spread a single atom in a superposition state, which is of this size. Yeah, that's really amazing. Yeah, so that is it's a quantum mechanical state, which is really large. Yeah, so that is like a macroscopic scale. It's a common scale. And they show all the details, and they prove that again, it behaves according to quantum mechanics. It's a matter wave. And atom interferometry, of course, has a very long history. So that's not the very first atom interferometer, but it is the, the largest, of course. Largest in the sense, so the question is big, does it mean large or massive? Of course the atom is comparably light. Yeah? The mass of the atom is much smaller than things like macroscopic things. So now the question is, if you want to do the same experiment with something which is really as massive as things in our everyday world, yeah. So you have to try to do the same type of experiment but with different objects, and that is this stuff here. Maybe as the last slide. That was the experiment I was involved with in Vienna. So not in '99. I'm not that old, but basically a follow-up experiment of this. And that is again the same matter wave interferometry experiment, but you do it with this guy here. Does any of you know what this is? This molecule? Huh? I didn't hear. Yeah, it's carbon. Yeah, the buckyball. Yes, exactly. So it's a carbon C60 Buckminster fullerene. So it consists of 60 carbon atoms, and it really looks like a little football. Yeah, it has the structure of a football, but it was invented by nature, not by the FA or I don't know. So 60 carbon atoms, and the size of this is roughly a nanometer in diameter. It's very stable, and the name Buckminster Fuller, some of you may know this. Buckminster Fuller, he was an architect, and he was inventing these geodesic domes, yeah, these large buildings which they still use in Antarctica and on the moon maybe. Very stable structure, and he was discovering the structures without knowing that this 60 is existing, because he was looking for a very, very stable mechanical construction to build these huge domes. 1 minute left. So now that's a very stable molecule. It has about the mass of 700 hydrogen atoms. Yeah? So that's much more massive than the atom which I showed you before. And now the experiment here is to do this matter wave. So basically the C60 comes out of this oven in the beam, which is along this arrow. Then you have some beam preparation stuff, which I ignore for now. The important thing is that you have the grating here, which is a nanofabricated grating, silicon nitride, and the slit size is about 50 nanometer. Yeah, so you have now this grating, it's like a comb. Yeah, and you take the C60 stuff and you shoot it. You do the manipulation to prepare the wavelengths of these molecules, and then you have a detector which helps you to detect this interference pattern. Yeah? So the way it works is you basically can position this in different positions transverse to the beam direction, yeah? And then you have an ionization laser which is basically ionizing the molecules at the given position of the detector, and then you count clicks. So you basically set it at a position, and then you measure for a minute, you move it to a next position, you measure again for a minute, and that gives you the red balls here, and then if you do it systematically, then you get the interference pattern. So that means that's the experimental proof that even a comparably big molecule, yeah, C60 fullerene, is still behaving according to quantum mechanics. It's still showing this matter wave character, it's still showing this interference. Yes. I think with this I will stop. And thanks for your attention, and of course I'm happy to answer questions.
Okay, fantastic. Thank you once again, Hendrik. Does anyone have any questions for Hendrik? Go on, one at the back here.
Okay. I remember when I was a kid hearing an open university talk, and a quote from it really stuck in my mind. It said on the way past the other thing, it may be that there is no need for particles at all. It may be that everything is just out there waving.
Yes.
Do you think we need particles? Is everything just waving?
That's a very, very good question. Actually, I personally think no. I think it's, I would say even more. I would say that the concept of the particle is really weird if you think about it. Yeah. So if it's really something like a ball, yeah, I'm pretty sure that this does not exist if you go really to small scales. On the other hand, I can easily imagine that things are waves if I go really, really small. So I think I have a problem with the concept of a particle. What is a particle actually? And I think what somehow is missing, and where I don't have a good explanation, is how are particles actually created out of waves? Yeah? So what is the mechanism for this? must have something to do with, you know, what people call collapse of the wave function and so on. But yes, yeah, could be. We don't know for sure. And I think the interesting thing is, if I can elaborate a bit on your point, is that actually the theory which should help us to answer this cannot do it. So quantum mechanics, which is the theory of the small things and the theory of, you know, using wave functions and describing also this matter wave interferometer, they have no answer. Yeah? They don't know. I mean, quantum mechanics cannot tell you if it's a wave or a particle. Yeah? It is playing with this duality. But I think, you know, it would need somehow a lower level or a more basic theory to answer this question really. It comes, in the end, it comes back to the question, what are the, you know, essential building blocks of nature? And we don't know. I mean, I have to say that's my personal point of view, yeah? Particle physicists would kill me, I guess. They would say, of course, it's, you know, you have the field, you quantize the field, and then you have your quantum particle.
It's good. We still have questions in science. Any more questions from you guys? Well, okay. Well, you asked the question that I was going to ask, so that's fantastic. But if you do have questions for Hendrik, come and approach him later. Who was it who correctly answered that it was a single photon that was being used and not? That wasn't. Okay. Well, you should definitely come to us and talk to us about a T-shirt then. And I think somebody got the buckyball as well. So yeah, the guys on that table are doing really well for T-shirts already tonight. So thank you. Yeah, come and find one of us in the Pint of Science T-shirt. Similarly, I have to tell you this. We are taking photos tonight. So again, if you have problems with photos being published for future Pint of Science publicity in any way, then again, come and talk to one of us in the T-shirts, and we'll make sure that that doesn't happen. On the subject of admin, if Hendrik manages to start a fire or something like that, then we do have a couple of fire exits. We've got, along with the main entrance, we've got a fire exit here, and we've also got a fire exit down at the back by the staircase there. Sorry, say that again? Both, I like it, splitting the wave function, yeah. If you could run for all of the fire exits at once, that would be fantastic. Okay, so this is good, I can see you guys are a good audience, this is great. We've also got a few other opportunities to win prizes tonight. So we've also got an Ask a Scientist question box up again. We got quite a few good questions last time. In fact, some of them were so good that we're thinking we might need to give prizes out for these questions. So if you have a good question, if you can stump us and ask a question that a scientist in the room cannot answer, then there's a T-shirt in it for you as well. Other things we got running tonight. We have got a question on here, which is a guess how many question, and we want you to guess how many. I think it's what was the maximum number of single photon qubits have been managed to. There we go. I've actually written it down. So if anybody knows what the maximum number of identical single photons used for a quantum computation in a photonic circuit is. Difficult one to guess. Oh, I don't believe you know the answer. If you do, write it down. Or come and talk to us about the question. The question is on the sheet. The sheet is by the silver box. Right. Fantastic. Thank you, Nathan. What else are we running tonight? We've also got bingo. You guys all received bingo cards in the doors, and I think you've been told what to do with them. But if not, it's not bingo where we're calling. Just if you hear any of the words on your sheet at any time, then fill it out and shout bingo anytime, even if it's during a talk, then shout it out, and again, T-shirt in it for you. So I'll give you a few for free. Atoms and quantum. So if any of you got atoms and quantum on your sheet, fill it out, do that. Okay, fantastic. So if nobody else has got any questions, then we're going to tie it up there, have a short break, and then we're going to start again for Ian at 8:15.